Okay, so sorry about the delay. We are now going to talk about star formation. So I understand there was no one was going to introduce me, so I was supposed to introduce myself. So let's start at the beginning. So my name is Fred Adams. I'm a professor at the University of Michigan in physics. I do astronomy as well. So where I'm coming from is that in the 1980s, I was a student of Frank Hsu, who's an important person in this subject and in this institute. And we jointly, the group, put together a theory of star formation, which lasts until today. So what I want to do today is I want to give you a lecture on star formation. Now, star formation is enormous as a subject, right? So we cannot cover everything in 1 hour, okay? So I'm going to focus on one particular aspect of the process, which is focusing on what we call the 4 stages of star formation, which is the, as you'll see, this will make more sense to you as we go through this. This is the phases when we go from the just before the collapse of the star to the pre-main sequence phase, and it's going to focus on low mass stars. So we're going to consider the formation of low mass stars 1 star at a time. Not global star formation in galaxies and so on. That's a very important subject because it's just not what we're going to do today. Okay, so you'll see what I mean as we go on. So to be clear, what you should think about is that the galaxy is this great big machine. There's this ecological cycle of star formation and mass. So molecular clouds produce stars. They evolve into pre-main sequence stars, end up being main sequence stars, and then they die. Some die by supernovae, most die by just having outflows, mass loss, and becoming white dwarfs. They return through these mechanisms, much of their mass back to the interstellar medium. The interstellar medium then makes new clouds, and round and round and round we go, okay? So that's sort of the big picture that the galaxy's doing. It's doing this whole cycle of stars and star formation and stellar birth and death. Now what we're going to talk about today is just one little segment from here to here, where we go from not actually the whole cloud or the whole cloud formation, but rather just a little part of the cloud to the actual formation of the pre-main sequence stars. Okay? Now, like I said, in the 80s, we put together this picture of how star formation works, and in a nutshell, it works with these 4 stages. You see that in 1986, when these things were drawn, our graphics are not as good as they were today. But this is sort of the classic picture. Okay, so what happens? Well, star formation actually takes place not in the molecular cloud, but rather in the small subcondensations within the cloud that we call molecular cloud cores. Those are depicted here schematically as these little dots. Okay? So there's a cloud core that we're going to talk about. The cloud cores evolved by removing their magnetic fields and becoming more and more centrally concentrated. They then reach a state where they collapse. We think they collapse from inside out, where the inner portions fall in first, and at the very center of the collapsed flow, you form a stellar-like object with roughly stellar dimensions, 2-3 times the radius of the sun. Because the collapse has angular momentum, most of the material actually collects in a circumstellar disk around the star and then works its way from the disk onto the star. The size scale, as we'll see over and over again in this talk, the size scale of these disks is roughly solar system size, so 10 to 100 AU. And then this whole star and disk is embedded in an infalling envelope of mass, of gas and dust that's falling on it from a much larger scale. Eventually, actually fairly early on in the process, the star is able to generate a very powerful outflow. The outflow, combined with the angular momentum considerations, ultimately, and perhaps through some other processes, separate out the star and the disk from its environment, and we're left with a young star with a disk around it. And it's in this stage, the star and disk stage, that planets form. I know that a lot of you have projects. Many of you are doing projects that are related, at least the list of them has a lot of disks and planets on it. So what I'm going to do for your lectures today is I'm going to talk about the actual star formation process today, and I'm going to talk primarily tomorrow about the disks and the planet formation process. So it's a little bit different than what's listed. So we're basically doing star formation today and planet formation tomorrow, and the circumstellar disk will be the sort of thing that ties the 2 things together. Now, In the 80s, just for historical reasons, we sort of considered one star forming at a time. We actually know, and this will come back a few times during the course of our discussion, we know that stars actually form in groups and clusters. So this process takes place within star-forming regions that are actually much larger, that contain hundreds or even thousands of stars. But on the individual level, this is still the story. And then once you get down to the size of the disk, we form planets on a much smaller scale, okay? So we can update the graphics. I had AI make this version of the plot last week. It doesn't change the story very much, okay? So let's get into some of the basics of the problem. So classically, one of the problems with star formation is called the angular momentum problem. What the heck does that mean? Well, if you look at specific angular momentum, it has units of centimeters squared per second. And as you know, unless you do something and have torques, angular momentum is conserved, okay? So if you just look at a molecular cloud and you measure how fast it's rotating and you measure how much angular momentum in it, it gives you this much. The specific angular momentum, the molecular cloud material, is 10 to the 24 in CGS units. You don't care about the exact units, you just know that that's a big number. Now, if you actually look at a star at breakup, so you take a star like the sun and you rotate it as fast as it can before it falls apart, the maximum amount of specific angular momentum it can have without breaking apart is 10 to the 18 in these same units. So here's the deal. This number is 1,000,000 times bigger than this number. That's a problem. In other words, if you have molecular cloud material and you let it collapse and you don't do anything with a specific angular momentum, the angular momentum you have is 1,000,000 times too big to put into a stellar-sized body. That's the angular momentum problem. Now, in between, as we'll see, the molecular cloud core, which is an intermediate scale between the scale of the whole cloud and the star itself, has an intermediate value of the specific angular momentum. So, spoiler alert, what we're going to see is that the angular momentum process, or angular momentum problem, is solved in two steps. One is when we go from the cloud size to the core size, we lose a certain amount of specific angular momentum. And then when we go from the core to the star, we lose another amount of angular momentum. When I say lose, we don't really lose it, we transfer it. Because angular momentum is ultimately conserved, but any given piece of mass that has angular momentum can lose it by transferring it out. Okay? So loss means transfer. Okay? Now there's a second classic star formation problem, and that's called the magnetic flux problem. So basically, if you have a magnetic flux or a magnetic field, it can support quite a lot of mass. Long story short is that the fields that we see in clouds are measured in microgauss. 10 to 30 microgauss is the typical number. That doesn't sound like a lot. As you know, if you're sitting here at the surface of the Earth and you have a compass, ain't nobody actually use a real compass anymore because you all have phones, but nonetheless, if you had a compass, it would point north. And the reason why it points north is there's a magnetic field, and the size of that magnetic field is about 1 Gauss. Turns out the sun has a field of about 1 Gauss. Jupiter has a field of about 7 Gausses. So planets have fields of order of Gauss, and stars have fields of order of Gauss and bigger. This is only microgauss, or 1030 microgauss. So it turns out that that's actually a lot. On the large scales that we're talking about, even a 30 Gauss field can support 1,000 suns worth of material, and this is a problem. If you were to take that large scale, that large magnetic field, and squeeze it down to the size of a star, then the magnetic flux would be enormous. And that can't be because that would be such a large magnetic flux that the magnetic pressure would overwhelm the self-gravity of the star and it would fly apart. In other words, you can't do it, okay? So, long story short again, you must get rid of magnetic flux in order for stars to form, okay? So we have two problems. If you want to take molecular cloud material without doing any physics, but just doing order of magnitude considerations, if you want to make that material and squeeze it into a star, you got to get rid of the angular momentum and you got to get rid of the fields. Otherwise, you'll never make a star, okay? So whatever star formation process you put on the table, whatever star formation process you consider, you have to consider those two problems. And what it means is something very profound, even though you don't know the details. These two considerations are actually not automatic. It's actually kind of difficult to transfer angular momentum out. It's kind of difficult to remove magnetic flux. And what that means is that star formation is fundamentally an inefficient process. In fact, we see it to be inefficient. And the way to state that is that if you take molecular cloud material, you can calculate a free fall time. During one free fall time, only about 1% of the material is actually processed in the stars. 99% of it is not. So star formation doesn't happen all in a free fall time, all automatically, all efficiently. It's rather inefficient, it's rather slow. Part of the reason is what we just saw, that we got to get rid of angular momentum and magnetic flux. Okay? So we're going to get into a little bit more detail as we go. So there's actually two ways to get rid of magnetic flux. One is you can diffuse the fields outward. So the process of diffusion will just move magnetic fields out. And you can also have reconnection, where magnetic field lines reconnect with each other and short out the field. Now, for those of you who are physicists, there's actually a third way to get rid of magnetic fields. And that's if our universe had magnetic monopoles, the magnetic monopoles could short out the field. But it turns out we only have one monopole in our whole universe, and that's not enough to actually play a role. So we're only going to consider these two processes in star formation. Now, here's the deal. To zeroth order, the diffusion process is more important. And here's why. In order for the field to matter, it has to hold up material. That's why it matters, right? Now, think about it. How is it that the magnetic field actually exerts a force on the material? Well, it can only communicate with charged particles, right? But most of the molecular cloud is neutral. In fact, the ionization fraction is kind of like 1 part in a million. So how is it that a magnetic field, which is only coupled to the ionized component, can exert a force on the largely neutral gas? The reason is that the field is tied to the ionic component, and the ions exert a force on the neutrals. But in order for them to exert a force on the neutrals, they have to slide past it. And in doing so, they exert a force on the neutrals. But what that means is, and again, this is pretty profound, magnetic support is synonymous with loss of magnetic support. In other words, in order for the magnetic field to support the cloud, you have to have motion between the largely neutral stuff and the ionized component, which means the fields are necessarily moving outward. And that's a diffusive process. So if you wait long enough, the fields will all go away. The problem is you've got to wait a long time. Now, the way it works, in a nutshell, I'll give you the simplest possible version, which takes us back to 1983 of all times. If you just write down a theory for a one-dimensional molecular cloud. So I have just a slab of material. This is the midplane, density increases up and down, gravity's pulling in, the field is supporting the gravity, and the field is pointing this way, but it's exerting the force this way. So this magnetic field configuration, which is just a toy model, is supporting the cloud. And what you see is that in order for the force to exert up and down, there has to be motion between the neutrals and the ions, which are tied to the field. And there's a constant that sets the coupling. The force is given by some interaction rate times the density of the two components and the relative velocity. You see that the relative velocity between the ions and the neutrals has to be non-zero, otherwise you don't get support. There's a dimensionless quantity, which is sort of the ratio of how much gravity and how much coupling you have. And for typical values in a cloud, it's about 0.2 or 0.18, which is less than unity, okay? If it were really, 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 really small compared to unity, then this whole thing would evolve quasi-statically. It's small compared to unity, but not that small compared to unity, and that will turn out to be important later on. Okay, so when you do the math, and we don't have time in this 1 hour lecture on all the star formation to do the math, I'm going to show you some equations. I'm not asking you to follow the algebra. I'm just going to point to the equations so you'll know what the heck we're talking about, okay? So what you do here is you set up the field in the configuration I showed in the previous slide, and then you ask what's its time evolution, okay? Its time evolution is given by this equation. Now, what I hope you will understand is that this is a diffusion equation. To remind you, if you don't remember what a diffusion equation is, you have a time derivative of, forget about rho, it shows up, but not important. Just consider B as your thing that's diffusing. You have a time derivative on the left-hand side, and you have a double spatial derivative on the right-hand side. That's the classic diffusion equation that you learn about in your differential equations course. You might not have liked it, but you did see this somewhere, okay? Now, so a couple weird things about this. Sigma is actually a log, or a Lagrangian mass coordinate, so it's sort of a weird spatial variable, but it acts like a spatial variable as far as the diffusion goes. The other thing is that the way the diffusion equations usually work is you have a derivative, the diffusion constant, and another derivative. The diffusion constant in this problem has a b squared in it. So that's where the weirdness comes in here, okay? The diffusion constant itself depends on the field that's diffusing. So that gives you a nonlinear diffusion equation. And that's important, okay? It means that, well, nonlinear equations are much more sensitive than other equations, so it means that you get a lot more sensitivity to your results. It will also be much more sensitive to fluctuations, as we will see, okay? So, the simplest picture would be that you form dense regions in a star-forming region. They're supported by magnetic fields. Magnetic fields will diffuse out if you wait long enough. And then once you get the fields to diffuse out enough, then you have enough self-gravity to collapse, and the star formation process can proceed, okay? So that's the basic picture. Now, the early version of this has some problems, which are listed here. One is that if you use the simplest version of the theory that I just gave you on the previous slide, it takes too long, okay? So, observationally, the way you see this is you can count the number of cores in a star-forming region. Some have stars and some don't. The ratio of how long it takes to collapse to how long it takes to get to the collapse point is the ratio of those two populations. What we see is that sort of equal numbers of star-forming cores and starless cores, which means that the starless core phase doesn't last much longer than the collapse time, whereas the diffusion, which I just said was slow, takes longer than that. We also see that when I look at the cores, even before they've collapsed, they're actually not static. They're actually moving in. They're moving in slowly, where slowly means about half the sound speed. So cores are not static things that sit around and then all of a sudden collapse. Cores are evolving things that slowly condense and condense and condense, and then they reach a state where they finally collapse. And we see these non-zero velocities at about half the sound speed that we have to account for. The other thing that's weird is that, as you'll see, when you diffuse the fields out of a core, the density profile of the core wants to reach a hydrostatic state. And for isothermal conditions, which means cooling is efficient, which it is in these clouds, you expect the density profile to be 1 over r squared. You don't care about the actual form, but it's essentially concentrated. But what we see is we see things that are not essentially concentrated. What we see are things that look like this, where you have this flat region that extends quite a long ways, and then it tapers off to a steep trajectory. So this is the density profile of a real bona fide observed cloud. And you see the data points are good. You know, we got a lot of them. And it follows a very flat top configuration. So the picture that emerges is shown here. This is the time evolution of the core. So what happens is that the star-forming region forms overdense regions. The overdense regions are supported by magnetic fields. In order for them to be supported by magnetic fields, the magnetic fields have to be diffusing outward. To start with, these core regions have a long, flat top. This is the density profile, so it's flat, and then it turns over. As the fields diffuse out, the core becomes more and more essentially concentrated, so the central density increases, the region that's flat decreases, and the region that's slopy increases. And that continues and continues and continues. The other thing I want to take your, or draw your attention to is that we measure in this plot the time before you reach the perfect 1/r² state. If you wait forever, the equilibrium configuration will be, of an isothermal core, will be rho going like 1/r², which is a perfect power law on this plot that goes all the way to 0. Now you never reach that asymptotic state, but your cloud core is evolving toward it. And as you get more and more flat top, time accelerates. The time to get from here to here, from here to there is 1,000,000 years. The time to get from here to the asymptotic state is 1/10 of 1,000,000 years. The time to get from here to the asymptotic state is 1/100 of 1,000,000 years, and so on. So again, what happens is that the cores start somewhere on the sequence, and they get slowly and then more rapidly centrally concentrated. But here's the key thing. They spend most of their time in this flat-topped configuration. Because it takes 1,000,000 years here and only 1/100 of 1,000,000 years here. So you see 100 times more cores with this configuration than this configuration. That's why when you look at the observations, you see this. But what's really happening is this. Now the lower curve shows the velocity profile of these cores with time. And long story short is that they're moving at about half the sound speed. Next up, I want to draw your attention to the mass scales that this picture gives us, okay? So the molecular cloud cores, which are the subcondensations that are ultimately going to collapse to form stars, generally have a configuration like we've shown, where I have a flat top central region, a steep region, but the steep region can't keep going all the way to 0 density. That would be ridiculous, because these things are embedded in some background cloud. So you have to reach a minimum density, okay? So here's the deal. At the moment of collapse, you have a central region that's flat-topped, and there's a mass enclosed in that central region, and that gives us a mass scale. That mass scale is tiny. It's kind of a few Jupiters in size. So it's not that tiny compared to you, but it's tiny compared to a star, okay? On the outside, once I reach the background density of the cloud, there's an outer boundary to the core. The mass enclosed in that outer boundary is 6, 20, 30 suns, depending on exactly where you draw it. It's much bigger than a star. One thing you should keep in mind is you tend to think of stars as being like the sun, because everyone says, well, the sun's an average star. Fun fact, if you look at the 50 nearest stars, here's a quiz for you guys. If you look at the 50 nearest stars, if the sun were average, it would be the 25th largest one, right? Right? What is it? If you look at the 50 nearest stars, how many are bigger than the sun and how many are smaller than the sun? What is the sun's ranking in mass of the 50 nearest stars? Someone's got to guess. You.
No, I have no answer.
You have to choose a number between 1 and 50. Again, if the sun were an average star, it would have the 25th largest. What do you think?
Yeah, I guess number 10. The sun is the...
It's the 4th largest one. So 9 out of 10 stars are smaller than the sun. So when we talk about star formation, we're not talking about generally stars as big as the sun. We're talking about stars smaller than the sun. Almost every star is smaller than the sun. The sun's actually kind of the big thing. I mean, you're all students, right? If you're in a class of 50 and you get the 4th highest grade, do you want a C? Because that would be the average grade. Of course not, right? You're just smiling, right? You want that A, damn it, right? Well, the sun is actually an A student when it comes to mass, okay? And that's one of the things that you should keep in mind. Okay, but anyway, point being that this mass scale here is actually quite a bit larger than the sun and quite a bit larger than the stars that form. And this mass scale in here is quite a bit smaller. The other thing that we see, let me just back up for a moment. So once we get to this state here, the core will collapse. And it will collapse according to a collapse model. We're not going to go through all the math of the collapse model, but there's a classic paper by Frank Hsu written as long ago as in 1977 that still holds today. And what you find is that the core collapses from inside out. The inside shells fall in first, and then the next outer layer fall in as you lose pressure support. And there's this expansion wave that propagates outward where each successive shell loses its pressure support. And what happens is that the trajectories of the infalling material become ballistic. And what that means is they lose their pressure support. Gravity wins over pressure, and things are basically in free fall in the center of this collapsed flow. The outside is still static, but the velocity profiles go from very low velocities to approaching free fall in the middle. The density profile in the spherical limit during this time has this characteristic r to the minus 3 has form. And the other thing that is important here is if you remember back to my previous slide, I'll show it to you. You have a tiny, tiny mass scale here, and a very, very, very large mass scale here. So after this little centrally concentrated core in the middle collapses, then you approach the solution I just described. But you don't care about the outer boundary until many, many solar masses of material have fallen in. So that means during the whole star formation process, when you're making a half a solar mass star, you don't care about the inner boundary or the outer boundary, even though there is an inner boundary and an outer boundary. And what that means is that the star formation process, the collapse process, doesn't give you a mass scale. It gives you a mass infall rate. In other words, the collapse process tells you how fast things are going, but it doesn't tell you where to end. And the scale that you get for m dot, that's the mass infall rate, is a factor of order unity times the sound speed cubed over g. That's typically 10 to the minus 6 to 10 to the minus 5 solar masses per year, which means it takes on the order of 10 to the 5 years to make a star, a tenth of a million years. So that's pretty quick compared to stellar evolution. So this is what I just said, the collapse process produces a well-defined rate, and the star formation is inefficient. So this mass scale that's given by the outer boundary is actually much bigger than the mass of the stars that's formed. So you always have mass left over. Now, we're going to run out of time really quickly here. So I want to I go through this next part very quickly. We talked about how you can form these cores by the diffusion of fields. It turns out that in addition to everything I said before, these star-forming regions are turbulent. So if I add turbulence to the nonlinear diffusion equation I showed before, I can let my magnetic field be the regular field plus 1 plus a fluctuation. I can let the density be the density field plus 1 plus a fluctuation. And I can put all these fluctuations into my equation, and I get this beautiful complicated equation. What that means is that the diffusion constant is more complicated, but it's nonlinear. Now here's the key thing. Suppose you have something that goes like b cubed. And suppose its value is just 1. So b cubed is 1 cubed is 1. That's your diffusion constant. Now let's let it fluctuate. So let's let the magnetic field be twice as big half the time and 0 the other half the time. Average is still 1, right? But if I average b cubed, I'm averaging 2 cubed and 1 cubed, 0 cubed, which gives me an average of 4. 4 is bigger than 1. You can quote me on that. And what that means is that any fluctuation tends to speed up the process. It does two things. So if you add fluctuations, you speed up the process. This is the time you get as a function of fluctuation amplitude. And the more you increase fluctuation amplitude, the faster you go. But also, you don't sample the fluctuations infinitely often because these are MHD fluctuations. You can't actually sample the fluctuations on the time scale shorter than the alpha crossing time of your core. So you only get a finite number of realizations of the fluctuations. And what that means is that each time you do it, you get a different answer. So long story short is that if you look at the non-fluctuating time scale, you just get one value, which in these units is 12. You don't care about the number, but you just get a value. If you add fluctuations, you move it over to be much faster. But you also get a distribution of values. And the distribution of values will have a tail that's really quite fast and a tail that's not so fast. And the ones that survive and readily collapse are those on the left side of this distribution. The point is you replace a single value with a shorter value that's a distribution. And that's what the fluctuations do to you. So now we can put this whole picture together. You start with some region, this might be a parsecond size, and the MHD fluctuations are producing little subcondensations. Those will be the cores. Those cores will show up somewhere on this plot with a long, centrally flat-topped configuration supported by fields. But support by fields is synonymous with loss of support because of the diffusion we talked about and the need for friction. So the ones that survive, and not all will, but the ones that survive will go through this sequence and become increasingly centrally concentrated. Now they won't go all the way to the singular configuration. At some point they'll collapse anyway, and then they'll join on to the collapse solution that we talked about, where the core collapses from inside out and approaches free fall conditions in the center. So this is kind of how you get cores to go through the collapse phase and ultimately collapse to form stars. Let's revisit our two problems, okay? So remember, we had too much magnetic flux. So the magnetic flux is lost in stages. By the time you get to the core stage, where you have a bona fide self-gravitating core that's supported by fields that can actually undergo the diffusion process, you've already lost about half your flux in a logarithmic manner. But in order for that object to not collapse, it has to be supported by fields, but if the fields are supporting it, they're diffusing outward. So over time, those fields diffuse outward and you get less and less magnetic flux. At some point, you start to collapse. What we don't know exactly is at the moment of collapse, exactly how much flux is left. There'll be a little bit. To zeroth order, we consider it to be small and not worry about it, but there will be a little bit, and that can cause some problems or issues later on. Now, you can kind of test this. If this is the case, then these star-forming regions, and this is sort of a parsec-size thing, so each one of these dots might be a forming core that'll form a star. When we look at the maps of these regions, we see that the cores are actually not static. They're not moving dynamically. If they're moving dynamically, they would be moving at a kilometer per second, just because F equals ma, right? We know how much mass there is. If they were in orbit, they would be moving at a kilometer per second. They're moving at 1/10 of a kilometer per second, which is about half the sound speed. So they're slowly moving through this region. You can say, well, if the magnetic field picture that I described earlier is the right one for describing the evolution of the core, then those same magnetic fields will actually determine a terminal velocity for the cores moving through the star-forming region. And the value you get is, after some algebra, 1/10 of a kilometer per second, exactly what you see. In other words, the fields that you see and are positing that will describe the core evolution are the same fields you need in the region to describe the motion of the cores themselves through the region. There's consistency there. And in both cases, you get the same velocity, about half the sound speed. The sound speed is 0.2, 0.3 kilometers per second, so half the sound speed is about 0.1 kilometer per second. That's the speed at which the cores are moving inward themselves, so it's the speed at which the cores are moving through the region. Both of those are the same value. Now, let's talk about angular momentum. Well, just like the magnetic flux is lost in stages, the angular momentum is also lost in stages. So by the time we get to the core start, and we've now got a complicated description of what it means to be at the core start, those things are not rotating with as much specific angular momentum as the molecular cloud itself. Remember, we had a factor of 1,000,000 in specific angular momentum to get rid of. We've already lost a factor of 1,000 by the time we get to the core stage. But these cores are still rotating. They're rotating with a characteristic velocity gradient of 1 kilometer per second per parsec, which is about 3 times 10 to the minus 14 radians per second, which means sort of a full rotation every 1,000,000 years or something. You put the whatever units you like. Okay. So these cores to 0th order are just rotating with this speed. Now it's not quite that simple, because the velocity gradients we see in star-forming regions are complicated. So the picture that emerges is shown here. During or over the region where we have this core that we are evolving into the centrally condensed state, when you measure the angular momentum, at one shell, the angular momentum vector seems to be pointing in one direction. And if you go out to a slightly larger scale, it's pointing in a slightly different direction. And when you go out to a slightly larger scale, it's pointing in yet another direction. Now, the picture that, or one way to describe this picture, is that you have collapsing shells. Each shell has this angular momentum with a slightly different vector. Now, the vectors are not completely random. They're all the same direction to within about 30 degrees, but they're also not aligned to within about 30 degrees. And that's due to the turbulent nature of what's left in this very messy cloud, and that will have implications for the tilt of the disks that form and ultimately can affect the plane of the planets that form later. Now, I'm going to have to speed up because we're going to run out of time. Quick question for you guys. We started a few minutes late. Do you want me to end on time? Do you want me to start or go an extra 10 minutes? What's your schedule after this? What's your preference? I don't know what your schedule is. How much attention span do you have? So. A little louder, sir? You have lunchtime. Okay. Well, I'll keep you, we'll just see how this goes then, because there's only actually 10 minutes left in the hour. So, long story short is that these cores will collapse. Now, we already talked about how the fact that when the cores collapse, the inside portion loses pressure support and becomes nearly ballistic. When I put rotation into this picture, I get this picture, which probably is not very enlightening to you, so let me just tell you what's going on. Okay. So if you have a ballistic trajectory with angular momentum, then, and you have an object in the middle, it's going to execute an orbit. And since these are these parcels of gas, which are pressure-free, are falling from a very large distance, they're going to be in a nearly parabolic orbit. But they'll be parabolic orbit in a plane, but that plane will depend on where you started. So it will be tilted with respect to, each one will be in its own plane. So what you got to do is you got to calculate the trajectories of each parcel in each of its planes and then add them all up together to get the density. And you can do this miraculously. You get these cool formulae. Again, this would be like an hour's derivation that we're not going to go through. But the point is that you actually got simple or relatively simple formulae for the velocity fields and the density field just by adding up these ballistic trajectories. Okay? Again, the algebra is not obvious to you, but the fact is, I'm just writing it down because we can do it, right? Now, what's key? There is one key point here. Given the angular momentum of the starting state, which is the rotation rate of the starting state, which I said is 1 kilometer per second per parsec, that's omega. For a given mass and density configuration, there's a centrifugal barrier in the problem. So if you're outside the centrifugal barrier, you don't have enough angular momentum to care, and to zeroth order, the parcels are falling nearly spherically. But once you get close enough in, there's enough angular momentum that you start to twist, right? That boundary between where it's nearly spherical to where it's highly non-spherical is called the centrifugal radius. There's a simple formula for it, but here's the thing. When you put in the sound speed that we measure, the rotation rate that we measure, and typical stellar masses, half a solar mass, the radii you get are 10 to 100 AU. So the centrifugal barrier in these collapsing cores is solar system size. Now to start with, they're a little bit smaller than a solar system, because 10 is less than 30. Remember, Neptune orbits at 30. And later on, they can be a little bit bigger, because 100 is bigger than 30. And the centrifugal radius grows with time as more and more mass accumulates. So this kind of makes sense. So the angular momentum problem is solved in 2 stages. Angular momentum is lost by the time you get to the core. The cores are rotating as I've loosely described. Those don't collapse, those cores don't collapse all the way to a star. They collapse to the centrifugal radius. They collapse to solar system sizes. Then, most of the mass falls onto this disk structure with a radius of 10 to 100 AU, not onto the star. So other processes, namely disk accretion, will have to move the material from the disk onto the star in order to make the star, and that's what happens. Now, there's another mass scale in the problem, and that is that because you're rotating, if you go far enough out, there's so much angular momentum that the material is already in orbit, which means it can't fall in. So there's an outer boundary set by this rotation. Again, don't worry about the algebra. Its value is, in this case, 6 times the mass of the sun. If I use a bigger sound speed, it could be 20 times the mass of the sun. In either case, it's kind of 10 times bigger than the stars you're making. Point being that during the collapse phase, you never get to this outer boundary, but there is, in fact, an outer boundary. There's another mass scale, too. Because you have this rotating infall collapse solution and things are falling to various radii, the centrifugal barrier tells you the outside size of that object you're forming, which I said is solar system size. But the material falling along the pole can get all the way to the origin, which is where the star is. So you can calculate how much of the material actually falls all the way to the stellar surface. And it's given by this cool formula here. But that doesn't mean much to you until you put in numbers. But when you put in numbers, the value you get is a couple percent of the sun. So only a couple percent of the mass will actually fall all the way to the surface directly. The other 90-some% falls to the disk and has to work its way from the disk onto the star. So there's two size scales that we've met. There's the large size scale given by rotation, which is much bigger than the star, and then there's a small size scale of what falls directly onto the star. Neither one of them is the right scale. What the star formation process does is it makes things collapse to a disk-like structure, a solar system-sized structure. And that solar system-sized structure moves most of its material, 90% in fact, from the disk onto the star, making the star, leaving the disk behind to make planets, which is what we're going to do tomorrow. Okay. Now, since we're a little bit low on time, I'm going to go through the next part of this kind of rapidly. One of the things that you care about is what do these things look like when they're forming. So the picture that we have emerging here is you have a star in the middle of the collapse flow, which is roughly stellar dimensions. It's typically 2 or 3 times the mass of the sun. Then there's a disk around it, which is typically solar system size. It starts at about 10 AU and goes to 100 AU. There's this envelope of material falling in. Outside the centrifugal barriers, the infall is more or less spherical. Inside it, it's highly non-spherical. And what you can then do is you can say, well, what do these things look like when they're forming? Now, in order to do that, we have to say, well, what's the luminosity? Well, to zero order, you're feeding material into the central region at sub-rate m dot. So the power you get is basically the depth of the potential well times m dot. And the depth of the potential well is gm over r star, because r star is the bottom of the potential well, and m is the mass that is accumulated so far. So this will grow with time because the mass is growing with time. So this would be the luminosity you would get if every proton fell exactly to the stellar surface. But of course, only a fraction do. Okay. So there's actually many different luminosity configurations, or contributions rather, that you can calculate. Some stuff falls directly onto the star and shocks and gives you luminosity. Some material falls directly onto the disk and shocks and gives you luminosity. Some material falls onto the disk, and since it doesn't know in advance that it's supposed to be rotating in a Keplerian way, it has to adjust its orbit and dissipate energy. That's called a mixing luminosity. You have a similar mixing luminosity on the sun, and then you have the disk accretion luminosity. The star itself also has an intrinsic luminosity. Now here's one of the things I want to emphasize to you. While the stars are forming, and this whole process only takes a couple tenths of a billion years, while the stars are forming, they're not burning anything, as in no nuclear reactions are taking place. The pre-main sequence time, which is the time it takes for the star to evolve from large radius to a centrally concentrated configuration where it can burn nuclear fuel, that's something for like 30 billion years. And my point is 30 million years is longer than 0.1 million years, by a lot. So when you're forming a star, it doesn't know in advance that it's supposed to have the right mass to burn nuclear fuel. But yet, somehow it produces objects, the star formation process produces objects that burn nuclear fuel. Okay? So while the star is forming, it has luminosity from the shocks that we just talked about, and it's starting to contract on the main sequence, on the pre-main sequence, excuse me, which gives you some intrinsic luminosity, but there's no nuclear power going on. Again, this just shows what I said before. You can measure the pre-main sequence time by the time it takes to radiate the self-gravity away, and that gives you the time it takes to contract. And the contraction time is about 30 million years for the cases that we are of interest here. So we have this following ordering of scales that you should kind of keep in mind. The star is at about 10 to the 11 centimeters. The disk is at 10 to the 14 or 15. The outer boundary of the collapsing region is about 10 to the 17. That's inside the outer boundary of the core. The clump itself is about a parsec, which is 3 times 10 to the 18 centimeters, and the cloud itself is about 10 times bigger. So you have this hierarchy of scales. And because there's a clean separation of scales, we can do the physics on each scale separately, which is kind of what I've tried to talk about. Similarly, there's mass scales corresponding to each one of those. Okay. And this, then there's also time scales. So again, the core formation time is about 1 million years. But you only see it in the centrally concentrated state for a fraction of that time. The infall collapse time is a couple tenths of 1 million years. Once you make these disks, as we'll talk about tomorrow, they live for 3 to 10 million years. And it takes 10, 20, almost 30 million years for the star to get around to burning its nuclear fuel. Okay, so now we're officially out of time. And this is the end of the first part of the time. So let me just tell you a little bit about a few things. So everything I've talked about so far is applicable to small stars. Once you get to bigger stars, 3 things happen. Okay? The first thing that happens is that you have to put radiation pressure into the problem. The radiation pressure actually keeps material from falling inward. Long story short is that the mass scale you need for radiation pressure to matter is about 7 solar masses. So for stars less massive than 6 or 7 solar masses, you don't need to worry about radiation pressure. Okay? Hold that thought. Second, we talked about the Kelvin-Helmholtz pre-main sequence time of being 30 million years. That's for a star like the Sun or smaller. As you make bigger stars, the Kelvin-Helmholtz time gets smaller. So there comes to a mass where the contraction time is as small as the formation time. Coincidentally, that's also at 7 solar masses. So stars less than 7 solar masses don't know about nuclear power. Those bigger than 7 solar masses do know about nuclear power because they contract fast enough that nuclear processing matters and radiation matters. And coincidentally, we know that stars less than 8 solar masses will end their lives as white dwarfs, or stars bigger than 8 solar masses blow up in supernovae explosion. So there's kind of a clean break at 7 or 8 solar masses between high mass stars that do supernovae, we care about radiation pressure, we care about nuclear power during formation, and low mass stars like the Sun, where we don't care about any of those things. So the paradigm changes. Now, I could talk about the radiation pressure in some detail, which I won't because we don't have time. What I want to leave you with is that the star formation process doesn't produce one well-defined mass scale. It produces a whole host of different mass scales. We have the gene's mass, which is much larger than the Sun. We have the mass that material falls directly onto the stellar surface, which is much smaller than the Sun. There's the critical mass of the core, which is 1,000 solar masses. There's the critical mass due to rotation of the core, which is tens of solar masses. You could define another mass scale using the eigenvalue of a magnetic thing, which gives you more like this scale. Significantly, all of the mass scales that the interstellar medium defines, and there's several of them, are either much larger than the star or much smaller than the star. Which means that when you have this collapsed picture that we've been describing, something has to stop it. You never run out of mass. Remember, you have 10 times more mass than you're ever going to put in the star. So something has to stop it. That's an open problem. Maybe one of you will solve it during your summer project here. The conjecture that we put forth is that outflows, which are powerful enough to fight or blow back the infall, will be part of the solution. But the details of how that works is left to be worked out. So I think this is a good place to stop. I'm only 5 minutes over. But what I want to do is I'll stop here. Tomorrow I will talk about disks, because remember, during this process, we form stars with disks around them. The disks have roughly solar system sizes. And it's in those disks that we make planets. So we will talk about planet formation tomorrow as well. Now, since I'm here, I will open up the floor to questions. You're free to either leave if you're hungry, you want to go eat lunch, or you can sit and ask me questions as long as you want. So I will end here, but stay for questions. So thank you for your attention. So any questions? Everything was 100% completely clear, right?
So, the photometric field, you say that they are important.
Can you speak up a little? You have to be louder than the air conditioner.
The magnetic field that you said that is important, but how does it even come from origin? Is it come from the primordial?
Oh, where do you get the magnetic field to start with?
Yes.
Well, that's actually a very good question. What we know is that on the scale of the whole galaxy is kind of pervaded by a 3 microgauss field. And what happens is that once you've got the gas in the whole galaxy on the galaxy size scale, which is a little bit less than we're talking about, it's 3 microgauss, that gets incorporated into the clouds, and then it's actually hard for field lines to end because we don't have any monopoles. So unless you short out the fields, there's no way to get rid of them. Now, the way you can generate a magnetic field is basically with current. So there are various astrophysical processes that produce currents, basically batteries, astrophysical batteries, produce currents that generate the fields. There's also various ways to generate magnetic fields in phase transitions in the early universe, which goes way beyond what we're talking about here. But one way or another, the fields end up in the galaxy. And then the galactic fields are what get incorporated into the clouds, and then some fraction of those get incorporated into the cores. And that's where we started our process today with the diffusion of those fields. Another thing that can happen is you get stellar feedback. So once you have a little tiny seed field, you don't need much, you can amplify it. And a dynamo is a way to amplify it. So a star is actually a very good dynamo. If you just have a tiny, tiny, tiny field inside a star, the combination of rotation and convection, which gives you sort of cells of current, can amplify that field up into the values we see. Now what we see is that stars like the sun, which are old and kind of boring, have 1 Gauss fields. But the T-Tauri stars, where they're young and energetic, they tend to have kilogauss fields, so 1,000 times the mass, or the field strength of the sun. So another thing that happens, bored to answer your question, is that when you make stars, and they have kilogauss fields, and the outflows that we talked about will spread those fields into the galaxy, and those will then contribute to the galactic store of background fields. So the whole process is very, very complicated. You put your finger on a very, very difficult question. But the short answer is that the galaxy has a tiny field to start with, where tiny means 3 microgauss, and that gets incorporated in the cloud, and then the rest is what we talked about. Was there another question? Did you have a question? No, you did. Okay. And then you, and then you. Yeah.
Could you please explain the diagrams about the magnetic flux loss? There's a few diagrams that show about the loss of the diffusion, magnetic field diffusion.
Well, the fields just diffuse outward according to the diffusion equation we put down.
Yeah, and there's a few diagrams that you showed.
Oh, do you know which? Well, I can page through to see what the diagrams are. Let me know when I get to it.